So it's a pleasure to have Charlie Wilson from Exeter, and he'll speak about dynamic properties of the sequence X to the n mod 1.
Thank you. And thank you, Thomas and Hannah, for the invite and opportunity to talk about something that I came across about a year ago that was also passed on by Simon and turned out to be a very fruitful and interesting area of maths. And hopefully I can do a good job of conveying that. So I'm going to talk about these dynamical properties of the sequence X to the n mod 1. And I had planned to spend a couple of minutes trying to really convince you guys that this was related to fractals. And Amir's done us all a service of meaning I don't have to do that. So thank you, Amir, again for this. What I was going to say was that I'm really interested in fractals, and so is my supervisor, and so is Simon, and lots of other people. And this seems to the problems that arise from this seem to kind of capture that fractals part of your brain, which it makes things interesting. Fractals is a reason these things are interesting too. So I guess I will, if my slides will move. There we go. So I'll give some motivation and a little bit of background and really ease in with the notation. So broadly speaking, we're going to consider some sequences that are going to turn out to be algebraically defined. And we're really just interested in the decimal expansions of these sequences. So if we just take the sequence, throw away the whole number part, and ask what's going on with this new sequence. And does any of the original structure that carried over from the previous sequence mean there's going to be anything interesting that happens here? So to kind of start off and ease our way in, we'll consider the simplest such case, which is xn is n alpha, for some non-zero real number alpha, which we're going to take as positive, although that's not the interesting part. So this is just repeated addition of some number alpha, and we're really interested in what's happening to the decimal expansion of these. So if we, to aid understanding, give this example where alpha is going to be root 2. So throughout the talk, when I refer to the decimal part, I might say x mod 1, or just use these curly brackets. So here I have the sequence of repeated addition of root 2 and the corresponding decimal sequence, or the sequence taken mod 1. And when I actually plot these out, this seems to be quite regular. It seems to be quite well spread out. So in fact, there's lots of maths done on this sequence in itself, in its own right. So this thing called Steinhaus's lemma and three-gap theorem, which say there's a huge amount of structure going on here. But for the purpose of our talk, I just want to talk about sort of uniform distribution and a few other properties like this. So we want to quantify what it means for this thing to be well spread out. And that leads us on to this definition of uniformly distributed modulo 1. And it's kind of what you would expect. So if we just fix some interval in 0, 1, the number of times that this sequence visits this interval should average out to be the length of the interval. So the thing that you'd expect there. And in this nice case of n alpha, we have the following theorem that's I've seen attributed to Whale, but there's also lots of other people who worked on this stuff in the same time in the days before archive when everyone did everything all at the same time. And so, I didn't want to put preference to one person. But there's this theorem that says for any irrational number alpha, the sequence n alpha is uniformly distributed modulo 1. So that's a very nice result and kind of confirms what we would expect. And of course, if we consider alpha to be rational, so some p over q, this thing becomes very uninteresting because it just visits these q many points and avoids everywhere else. And it's periodic, and it's kind of a bit boring and does exactly what you'd expect. And I should say here, so we're going to consider x to the n or alpha to the n. There's been lots of other algebraically defined sequences. So another one of interest is polynomials. So if I consider something like n squared plus root 2n plus 1 and ask about the distribution modulo 1 of this, we get a similar result. So in general, for a polynomial, as long as one of the non-constant coefficients is irrational, we get that it's uniformly distributed. And again, that follows on from work of Whale. So hopefully now the notation and the background makes some sense. So the original problem of n alpha, I think, is naturally found and also links to Diophantine approximation. Another, but I think just as natural a problem, instead of repeated addition, let's do repeated multiplication. So just do alpha times alpha times alpha to generate the sequence. And this is where I kind of have to pause and say, we're not actually going to consider that. We're going to consider something slightly more general, so this psi alpha to the n. So we just have this psi term, which it's just going to be some scalar multiple, so it's positive. And I kind of have to pause and say, trust me, this is the thing we want to consider instead. So the maths kind of works out that this is the thing that we're going to consider, but all the results kind of relate back to alpha to the n anyway. But when studying this thing, it's the more natural thing to consider, and the things that everyone's been considering since about 1910, 1930 for the problem. So yeah, so let's take an example here. So I have clearly picked alpha as 0.7 pi and psi as 1. And do the same procedure, write out the sequence and throw away the whole number part. And when I start to plot these out, we get this thing. So it's maybe not quite as rigidly structured as the n alpha case, but this thing spreads out. And as Amir stated in his talk, we get the following results. So I think it was the latter of these, the Coxman one that he stated. But yeah, I state them both here. So the first one by Wales says that if we fix this alpha bigger than 1, then for almost all of our real numbers psi, the sequence psi alpha to the n is uniformly distributed. And then there's the analogous result that came sometime later in the 1930s, that if I now fix the psi, then for almost all real numbers alpha greater than 1, the sequence psi alpha to the n is uniformly distributed modulo 1. And the proofs don't go through exactly the same. There's a few, they take slightly different directions, but both were done in the first half of the 1900s. And for the eagle-eye viewers, you'll note here that there's this almost all, or almost every, in the theorems. So I should state that almost every is with respect to the Lebesgue measure. And I guess the natural thing to ask is, well, do we need that condition there? So for the polynomial case or the n alpha case, that wasn't there. We've got an absolute statement. So why do we have that there now? And it's with good reason. So with that in mind, I present this example. So we pick alpha to be 2 plus root 2 and psi to equal 1. Same procedure, write out the sequence, throw away the whole number part, and we get this thing appearing here. So these seem to aggregate around 1. So I've only done the first 7 terms of the sequence here. When I include more, it just gets very cumbersome around 1, but they all go arbitrarily close and monotonically close to 1. And so if I introduce some notation so I can express this rigorously, we're just going to use this double line modulus to be the distance between x and the nearest integer. So it's very closely related to this curly brackets. It just means that I can say it tends to 1 and tends to 0 at the same time, really. And we can rigorously show that 2 plus root 2 to the n tends to 0, or at least it gets arbitrarily close to an integer as n goes to infinity. So there's a nice way of seeing that actually, that if we consider 2 plus root 2 to the n plus 2 minus root 2 to the n, the root 2 components coefficients are going to be the same, but positive and negative. So they completely cancel out. So that means that this thing is going to be integer valued for all natural numbers. And the second term is less than 1 in modulus. So as n gets large, this is going to shrink. And it's quite a cute way, I think, of seeing this. But taking a step back and looking at the whole problem now, this feels a bit strange that we can do something which seems quite random of multiplying a number. We expect that to uniformly distribute, and it has arguably the most opposite direction possible, the opposite behavior that aggregates around a single point. It limits to a point. And alpha being 2 plus root 2 isn't a standalone thing. There's lots of others. So that motivates the following definition of a Piso number. So a Piso number is a real algebraic integer alpha bigger than 1, all of whose Galois conjugates following itself have the modulus strictly smaller than 1. So I'll break that down a little bit. So being a real algebraic integer just means that alpha satisfies some monic integer polynomial, and its Galois conjugates are all the other roots of that polynomial. So I should probably add irreducible polynomial into that. So for the example of 2 plus root 2, this was a Piso number because its Galois conjugate 2 minus root 2 is less than 1, and that's the only Galois conjugate in this case. And it's been shown by Piso that anything that satisfies this algebraic condition must have that psi alpha to the n tends to 0, provided psi is taken from its number field Q of alpha. So anything that is a Piso number exerts this behavior that alpha to the n tends to 0 or 1, modulo 1. And then we ask about the converse. So we provided some examples that break this, and there's these 2 results. So the takeaway of this Gelfand one is that if this thing limits to integer very quickly, so specifically this quickly for some c, then we must necessarily have that this thing is a Piso number. This alpha is a Piso number, and psi has to lie in this field. And if we go one step further and say, let's just consider algebraic numbers, then the only algebraic numbers that exert this behavior, that psi alpha to the n limits to an integer, are Piso numbers. So this is completely classified for algebraic parameters. And indeed, if we're willing to say something about the rate of convergence, this is classified for all numbers. So I guess what happens if we drop this? And this leads to the following question posed by Hardy. Does there exist a transcendental number alpha bigger than 1 and a non-zero real number psi such that psi alpha to the n tends to 0 as n tends to infinity? And I'd love to say that I have an answer to this question, but this has been unknown for the best part of over 100 years now. So if anyone has an idea for this, this would be great. And indeed, very little is known in general about transcendental numbers raised to higher powers. So the distribution of something like pi to the n or e to the n, I believe is still unknown. But as is often the case when we have a long-standing unknown problem, lots of other partial results come along. So there's this really, really nice one of Vijayaraghavan, and I'll apologize now if I've butchered the pronunciation there. And they say that if you basically give me a sequence of target points and some epsilon error, then you can produce an alpha that will always be such that alpha to the n will be within epsilon of xn for all positive integers n. So this is a sort of hits the post almost. If we could let this this epsilon shrink, then we'd be fine. But this is a fixed epsilon. So we don't get convergence. We just get that it gets within this distance of it for all numbers, for all integers n. And not only does there exist an alpha, there's uncountably many such alpha. And in 1980, Paulinson showed that the set of such alpha is a full Hausdorff dimension. So there's a lot of alpha that do this. I should also add, I think Dubicus proved or demonstrated an algorithm to find such an alpha. I mean, it's not one that we can do, but he showed that in principle, if this algorithm was to run for infinite time, it would throw out the design alpha. And yeah, so I think there's 2 or 3 different proofs of this. One of them is quite a nice Cantor set argument as well. So then I think Simon passed on to my supervisor, or my second supervisor, Mark, that this problem, and we became really interested in being able to say something about this using dynamics techniques. So there's a whole host of results relating to this and a whole host of different techniques used. So Amir kindly pointed out some L2 flattening type results, and things using Fourier transforms to get quite nice statements about the uniform distribution properties. There's Wales criterion, there's number theoretic techniques to get statements out, but we propose some dynamics inspired techniques where there's a lot of air quotation marks, because it doesn't quite work to be dynamics. And really our motivation was we have these two results. So we know this thing's uniformly distributed, so it spreads out quite well. And if we fix some interval, it lands in that interval the right number of times. And we also have this result here of saying if we move the targets, we can still find points that do this. So we were thinking, well, what if we kind of have these targets but shrink them? Can we state anything about this? And that leads us on to this result. So if we consider the sequence psi alpha to the n as above, and these moving targets centered at gamma to the n of radius Rn, and we're going to think that Rn is going to shrink to 0. And we establish the following dichotomy. So if the sum of Rn is finite, then for almost every psi, the number of times psi alpha to the n visits these sets is finite. So that's an almost sure statement. And then we have the dichotomy result. So this is infinite. We get this thing called the strong Borel-Cantelli property. So the number of times psi alpha to the n visits an is proportional to the size and measure of those targets. So this limit is 1. And this is like an intermediary, well, it's a strengthening of uniform distribution, and goes some way of stating what the behavior is going to be like as we shrink these targets. So it's in the limiting behavior, and says that this thing's pretty well behaved. It does what we would kind of expect if this thing was like an independent random variable, and we get this sense that it acts quite randomly. I would say also from the dynamics perspective, which was the inspiration for this stuff, that even with quite strong mixing for a random for a dynamical system, we don't get this dichotomy. We often have to assume something about the shrink rate. So there's something quite special going on here with the psi alpha to the n and how this, we'll see, mixes, and how strongly this mixes to mean that we do get a full dichotomy, and we don't have to assume anything about the shrink rates. Okay. So with this in mind, I should probably motivate how we go about our direction, and how we apply dynamics to this. Because this thing isn't dynamical is the first big red flag. So we've established that for almost all real psi, if we define xn of psi just to be the fractional part of psi alpha to the n, xn of psi is uniformly distributed. We know this, but xn of psi isn't a dynamical system. So for a dynamical system, we just have some space and a single map that maps single points to other points. And importantly, if I have two initial starting points, if they get mapped to the same point after one iteration, they'll stay together forever in our system. This doesn't happen here, so it can't be expressed as a dynamical system. So if we consider these points, after one iteration, so x1 of psi apply to these, for this alpha value go together, but then x2 of psi, these things separate apart. So this thing isn't dynamic, but it has lots of qualities with a dynamical system. So we can't straight away apply anything from dynamics, but this thing starts to look measure preserving. So if we consider a fixed interval in 0, 1, and ask about the set of psi such that xn of psi lands in this interval, the measure of this set limits to the measure of the set. So it's almost like asymptotically measure preserving. I'm not sure if that's a pre-existing notion, but it kind of has this behavior that it, for large times, gets close to being measure preserving. And there's some other qualities like mixing that also seem to happen, which opens the door to us to try and shoehorn some of these techniques in. So our proof basically boils down into 4 steps, and I'll give some hand-waving picture-inspired proofs of each step. So the first thing is we establish this almost measure preserving statement. Establish the notion of mixing as well for this system. So I think lots of people are probably aware of mixing. This just basically means that the deterministic evolution of the system behaves statistically very close to independence. So things act like independent random variables, which are very, very nice and we can say lots about. And then we're going to frame this problem like a dynamics problem. So we start to look at this sequence of functions given by the indicators of the pre-image set, and then use sort of standard lemmas that we would use in dynamics to provide the strong Brelkin-Telly property, and tweaking them where relevant, because as I said many times already, this thing isn't dynamic. Okay. So we first asked, what do these pre-images look like, which leads us on to the measure preserving statement. So I just give an example here. So we map psi alpha to the n for this alpha parameter and let n equal 4. As expected, we're just going to get this almost like doubling map type thing. But here it's not going to be alpha to the n isn't an integer. So we get this small amount in the bottom right hand corner, which doesn't map perfectly. We just get a fragment of this one. And this is where the almost measure preserving comes in. But noticing this, if we ask about the psi that lands inside the target quarter to a half, this is very regular. Like, this is just some interval repeated several times. And we can go away and calculate the size of this quite easily and work out it's just the size of the target over alpha to the n. And we get roughly alpha to the n of them. And that leads to the measure preserving property here. So if I have some fixed target set, I look at the pre-image set, and the measure of that does limit to the measure of the target. And we provide these nice bounds, which ensures we don't just converge quite quickly, we converge exponentially quickly, which is really, really key to our proof. Okay. So I hope that I've somewhat convinced you that this thing's limits to be measure preserving with some hand waving and pictures. Hopefully I'll do the same now with the mixing conditions. So all I do here is take these pre-image sets and plot them out for several n. So this is just the bottom set here is the pre-image set we saw before, and with the other pre-image sets as well. And we see the behavior of these is, for large n, we'll get alpha to the n roughly of them, a very, very, very fine and small width. So these things start to look very grainy, which means that they spread out a lot. So then if we kind of intersect one of these pre-image sets with another set much earlier on, because of how grainy and fine and sort of dusty this goes, the intersection is very well behaved. So the intersection behaves kind of like the product. So if I look at the measure of the intersection, that looks like the measure of the bottom set multiplied by the measure of the top set, which is precisely what we want for mixing. So that leads us on to this statement. So for a sequence of sets AN, so I allow the shrink rate here. This has width phi n. Then the measure of this intersection subtracted by the measure of the product of the measures, can be bounded by this. And this is really where the strength of the mixing comes in, because not only do we have this exponential term on the bottom, we also get the size of the set up here. And that's really important. So in regular dynamics, often we don't assume that this the size of the set appears in the right-hand side, so you can get some issues appearing when you have small sets throwing out big intersections and things like this, or bigger than they should be intersections. But here we have that term, so that really controls things in a strong way. So this is where we apply this key lemma, which appears in the Harman book. There's a ton of variations of this. I think there's a Sprinchuk one, but this is where we're going to combine our results together. So what does this lemma say? This says if I have a sequence of functions, and the functions get very close to the mean. So in what sense? Well, the average of the square of the distance grows less than linearly compared to another sequence. So this is really, really very strong that something squared grows less than something linearly. Then we can get this statement about almost every. So it's a tool to go between metric statements, the statements about measure theory, where we kind of reduce the noise by using measures and averaging things out. And provided this thing averages out really well, then we can swap that statement for an almost every statement here. So it's a really useful tool used in dynamics, and we can apply that here. So I've done something which I get told not to do, of like trying to apply the things we do into the lemma so it kind of makes some sense, I hope, and so it's easy to see. So the functions we take is just a pre-image set. And we see that the measure of the pre-image sets is just going to be bounded by the measure of the original sets up to some constant because of this measure preserving statement we established before. And now when we expand this square term out on the left-hand side here, this is just going to generate this here in our context, because we're considering indicator functions. So when we integrate these, they just become the measures of the sets. And this looks exactly like what we had before for the mixing condition and the measure preserving condition. So this first term on the top line is just mixing. We bounded this nicely before. And on the bottom, well, we can, the first term on the bottom is very, very similar to the measures of the original sets by the measure preserving property we had before. And we can neglect the second term because it's negative. So combining this all together, we'll get the sum of the indicators equals the sum of the measures of the targets plus some big O term, which is going to shrink much quicker or grow much slower than all the other terms. So when we divide through, we get the last line here. Because by just adding up indicator functions, that's just the same as counting the number of times I return to these sets. Okay. So I think I still have a couple more minutes, but I won't go over. And so this establishes like a strong Borel-Cantelli property for these. And I think this has a natural correspondence to the sort of pre-established results, sort of number theory inspired results about uniform distribution, because we can kind of motivate that by shrinking sets. But we also established some more results that are kind of more inspired by the dynamics. So we established a strong Borel-Cantelli property, and then we can, once we have this, there's really standard techniques from dynamics to say something about hitting times. So if I have a very, very small set, and I ask how long does it take for xn of psi to actually hit that set, I can make really strong statements about that too. And the same for eventually always hitting. So instead of me asking specifically that I want xn of psi to land in an, I just asked do any of the x of psi, so x1 of psi, x2 of psi, etc., land in this set, and make statements about this, which I guess is maybe less directly motivated by number theory, but it's natural in dynamics. And Mark and I, so I should say all of this was joint work with Mark. I think I said that at the start, but I can't remember. We make the analogous statements for returns. So if I start at a point, I don't just ask, can I reach something over here? I ask, do I get close to myself? So do I land back close to that? And it's got a subtly different dynamical flavor, but we're able to tackle these problems as well. And then later on in the paper, we consider general sequences. So psi of n to the theta, for instance. So I think these are also well studied. Maybe there's less. I think there's a lot of work been done in this field because of the problem of Hardy. So I don't think there's any long-standing problems of the same maybe caliber as that, or been unknown for such a length of time. But they're equally interesting problem to consider. The issue here we have is we don't have the same level of mixing, and we don't have quite the same measure preserving statements. So we have to be careful about how we shrink our sequences and shrink our sets that we're trying to land in. But we're able to say something about those. So I think this is nearly time. So we're thinking about also applying this to get other statements like Poisson recurrence laws, Poisson laws for them. But this is something for the future. And then maybe one day solve Hardy's question. But I think that's a nice point to wrap up on. So thank you again, Thomas and Hannah, for the opportunity. And any questions? Great. Thank you.